All right, let's start doing some calculus. The first part of calculus is called differential calculus, and that deals with the derivative. And what we want to do here is define the derivative and use that definition to find the derivative of a function. First of all, for a little bit of context, in about 1665, two people, Sir Isaac Newton and Gottfried Leibniz, both invented calculus. They were in different countries. Newton was an English scientist, and Leibniz was a German mathematician. They weren't working together. They both worked on these ideas independently and developed them at about the same time, which led to a little bit of a rivalry between the two. But initially, what's important for us is their notation. See, Newton was a physicist. He was studying motion and definitely looked at the derivative as a rate of change. Notationally, he used this dot notation where he would put a dot over the top of a y to indicate y prime, or the derivative of y. Over time, that has led to this prime notation where we use just this apostrophe as y prime. Using functional notation, if we were dealing with f of x, then the derivative would be f prime of x to indicate the derivative of f. There is this idea of a second derivative, which would just be two apostrophes there. Now, Leibniz, on the other hand, was a mathematician, and he looked at calculus as a way to unify logical thought in many different fields, like between geometry and algebra. But when it came to the derivative, Gottfried Leibniz definitely looked at the derivative as being the slope of the tangent line. So the change in y over the change in x. However, he was looking at tangent lines and not secant lines, and he let those changes get infinitesimally small, and that turned into what we call the differentials, dx and dy. So the slope of the tangent line being dy over dx. So notationally, these can be used interchangeably, either this prime notation or the dy dx notation. With Leibniz, if we were talking about a specific function, say x squared, we would say d dx of x squared, being the derivative with respect to x of x squared. Now first, we're going to use Leibniz's definition of the derivative as the slope of the tangent line to take a look at how we can calculate that. So here I have this function, y equals f of x, and I've identified this x value. So we do have this point, which would be x, f of x. Now, when it comes to the tangent line, a tangent line is going to intersect the curve at just one point. However, it just kind of skims that curve. It doesn't cut across the curve at all. We know that if we were to extend this line, eventually it would move along it and cut through the curve over here. But locally, this is what our tangent line is going to look like. Now, in order to get to the tangent line, to try and find that slope, I've only got one point that I'm dealing with. In order to deal with the slope, I need another point. So what I'm going to do is I'm going to let x change. All right, so I'm going to have this change in x here, which we call delta x. And that will get me out to this x value of x plus delta x, being this point right here. Right. Its x coordinate is x plus delta x, and its y coordinate be the functional value there. Then what we have is called a secant line, where we're connecting these 2 points that run through our curve. And we can find the slope of that line. That's a real Algebra 1 thing to do. All we have to do is take the 2 y coordinates, f of x plus delta x, and subtract off f of x. Then do the same thing in the denominator. I'll take the x coordinate of that point, x plus delta x, and subtract off the x coordinate of that first point, just x. And we have this simplified expression, f of x plus delta x minus f of x, all over 2x's canceling, Leaves us with just delta x in the denominator. But the problem is that that is the slope of that secant line, which is not a tangent line. How we get to the being a tangent line is I'm going to let that point move closer and closer to our first point. So if I let that point move over to here, then our secant line has moved a little bit. And what else has happened is that our delta x has gotten a little smaller because our x coordinate has now moved over to here. But what I want to do is let that point move even closer, get closer and closer to that original point until it lands directly right on top of that first point. When that happens, then we'll end up with our secant line changing from these approximations of the tangent line into the actual tangent line itself. But as we move that point closer and closer to the original point, in essence, what we're doing is letting that delta x get smaller and smaller and smaller until that x plus delta x lands right on top of our original x. Well, what that means for us is that delta x, that actual distance, has gotten so small that it's actually 0. So our first derivative is going to be that expression that we just came up with, because that's the slope of the secant line. And when it's just like this by itself, that's the slope of the secant line. But when we let delta x get so small that it turns into 0, we do that by taking the limit as delta x approaches 0, then it becomes the slope of the tangent line, which is our derivative. And that's where this definition of the derivative comes from. So before we put it to use, just kind of getting used to the notation of it, if I want to find g prime of x using this limit definition, it would be the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. If we're talking about the derivative of the sine of x, we still are going to have a limit definition as delta x approaches 0. It's just we know what the function is, so that would be sine of x plus delta x minus sine of x all over delta x. Working the other way, if we see the limit as delta x approaches 0 of 4 to the x plus delta x minus 4 to the x all over delta x, then we know that we're talking about a derivative. Right? This sort of limit to start things off would definitely signal to you that we're talking about the derivative. But the derivative of what function? Right here, the derivative of 4 to the x. So now we can practice actually calculating a few limits to find those derivatives. When we're talking about f of x being x to the third, if I want to find the derivative of that, we're going to go with the limit as delta x approaches 0. First we'll substitute in there x plus delta x to the third minus x to the third all over delta x. Now, be very explicit as you go through your work. I've been emphasizing this, that you haven't taken the limit yet, so you have to keep this limit notation around. We are going to expand this x plus delta x to the third. So we'll have 3x squared delta x and 3x delta x squared before we get to the delta x to the third. All right, then we subtract off that x cubed all over delta x. The other thing, of course, is leave that denominator around until it's gone. People get very lazy and want to just ignore the denominator for some reason. But we're going to cancel our x to the thirds. And notice that every other term that we're left with has a delta x in it. So I'm going to factor that delta x out of everything in the numerator. so that it'll cancel with the one that's in the denominator. Hasn't canceled yet. That's why I still put that denominator there. But when I go through it term by term and I take that delta x out of our first term, we're left with 3x squared. When I take 1 delta x out of the second term, we're left with 3x delta x. And when I take 1 delta x out of that delta x to the third, we're left with delta x squared. And of course, like we said, those delta x's will cancel. And what we're left with is still a limit. So the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared. But the thing is, delta x is going to turn into 0. So right here in our second term, that delta x turns to 0. 3x times 0 is 0. And in our last term, delta x squared, that delta x is 0. 0 squared is 0. So we end up losing these last two terms, and the only one we're left with is what our derivative is, 3x squared. Let's try one more. Say g of x is 1/2 x squared plus 1, and we want to find that derivative. We're going to take the limit as delta x approaches 0 of this fraction divided by delta x, and in our numerator, we're first going to just substitute that x plus delta x, so 1/2 x plus delta x squared plus 1. And subtract from that g of x, which was 1/2 x squared plus 1. Next thing is to expand. We have not taken the limit yet, so I'm going to keep that limit around. We have not canceled the denominator either, so we're going to keep the denominator of delta x around as well. And the only thing we can do is expand, and expand this x plus delta x. So we'll have 1/2 here, and the x plus delta x squared is going to be x squared, 2x delta x, and delta x squared plus 1. We can also distribute our negative here, and we'll have minus 1/2 x squared minus 1. There's a little bit of canceling, of course, that can happen with this plus 1 and minus 1, but nothing else yet, because we still need to distribute our half into that one. So haven't taken the limit, keep the limit around. Haven't canceled this out of the denominator, keep that around. But when I distribute that 1/2, we have 1/2 x squared plus 1/2 times 2 is 1 x delta x, and 1/2 of delta x squared. And towards the end here, we still have the minus 1/2 x squared. It's nice. The 1/2 x squareds will cancel, and everything that we are left with has a delta x in it. So I'm going to factor that delta x out. Have not taken the limit yet. Have not canceled the fraction yet. But I am going to factor out that delta x. And so out of my first term, I'll be left with x. And out of the second term, taking 1 delta x out of there, I still have 1/2 delta x. Those delta x's will cancel here and here. So we're looking at the limit as delta x approaches 0 of x plus 1/2 delta x. Well, delta x is the only thing that turns to 0, which means this term is the one that turns to 0. And our derivative is going to be the limit of x plus 1/2 delta x as delta x approaches 0 is just x.